Okay, now we're going to define resistance. Resistance to the flow of current. I'm going to say that resistance is defined as voltage divided by current. This makes sense because if you need more voltage to get a given current, that means that you got more resistance. So voltage ought to be in the numerator. On the other hand, if you get more current for a given voltage, greater current for the same voltage is going to give you a greater denominator, therefore a lesser resistance. Does that make sense? Yeah. If you get more current for the given voltage, then you've got less resistance. And that should be fairly obvious. Now, the fact that this relationship is inherently linear, that is, you have a first power of V and a first power of I. It's linear with V. Resistance is linear with V and inversely proportional to the first power of I. The fact that all these are first powers took some work, took some important and precise experimentation. And a guy named Ohm did that. So we named the unit of resistance the ohm. 1 unit of resistance, 1 ohm, would go with 1 unit of voltage, which is 1 volt, and 1 unit of current, which is 1 amp. So the SI unit of resistance is the volt over the amp. Now, a volt is a joule per coulomb, an amp is a coulomb per second. When we divide a joule per coulomb by a coulomb per second, we get a joule second per coulomb squared. Now, an amp is a coulomb per second, so coulomb is an amp times a second. So what we get is here joule seconds over amp seconds squared. And the reason we go to this is that the amp is now a fundamental unit. The coulomb isn't. So the fundamental SI unit would be what? It'd be joules per amp second. And of course we can bring the joules down. Express the joule is a Newton meter squared per second squared, and articulate that and get everything down into fundamental SI units. However, joule second per coulomb squared, the coulomb's a little more intuitive than the amp, a little less complicated, even though we can't measure it as precisely. So we will use this unit for now, for most of our calculations. Okay. In other words, in any case, that's what an ohm is in the fundamental units. The one thing you've got to understand, though, is that if you multiply an ohm by an amp, you get a volt, because R times I equals V. If you divide a volt by an ohm, you get an amp. Now, we've seen that resistance depends on cross-sectional area and length. We've posed the question, okay, if resistance depends on cross-sectional area and length, and if you have a simple relationship among first powers, which in case of cross-sectional area and length makes very good sense, and again that length affects your electric field for given voltage, and cross-sectional area affects how many charges you're able to move. Don't like that statement particularly, but you get the idea. Okay, so if we have a simple proportionality involving cross-sectional area and length, it could be a proportionality where the resistance is some constant that will depend on the material, multiplied by cross-sectional area time and length, or multiplied by cross-sectional area and divided by length, or multiplied by length and divided by cross-sectional area, or divided by both length and cross-sectional area. Which one of these makes sense, makes the most sense? Okay, well, as we've seen, longer implies more resistance, so that the length had better be in the numerator, which it is here and here. Greater cross-sectional area implies more current, which means less resistance. Well, then the cross-sectional area is not going to go in the numerator. It's got to go in the denominator, and that leaves us this choice here. Now, if we use the letter rho for that constant, the constant that depends on material that's different from gold than it is from silver, than it is from copper, etc. Okay, that's going to be our rho. That's called resistivity. That's what we're going to call our proportionality constant. So R is resistivity times length over cross-sectional area. And that should make good sense to you. This is our way of taking account of the length and the cross-sectional area. Again, greater length, more resistance. Greater cross-sectional area, less resistance. Greater value of rho, more resistance. We calculate the resistance of the wire in case 1 of our example in problem number 1. That we'll go on with that. We'll do another video on that. It'll be relatively short.